Hi, my name is Harvey, and today we're going to give you a presentation on the principles and applications of photoluminescence in defect analysis. So here is a table of contents for our presentation. So throughout our presentation, first we're going to talk about what is photoluminescence, and we'll go into more details into the mechanism of photoluminescence. And then we'll go into more details about the practice and the operation and the instrumentations of the photoluminescence. And finally, we'll use three examples to gauge the application of photoluminescence in different types of materials. So first, it's in conventional semiconductors, and then in a more unconventional conjugate polymers, and in two-dimensional materials. And then we'll have a conclusion that wraps up our presentation. So what is photoluminescence? Um, First of all, let's look at the effects of luminescence, which is essentially the emission of light from an excited electronic state. So what does that mean? Is that when the electron is stimulated by outside energy or reactions, it can be excited to a different energy level, and when it releases and relaxes, it will release energy, and a light will be emitted from the material. And there are different types of luminescence, including electroluminescence, which is when the electron is excited by electrical current or electrical field. And there are chemiluminescence, where the electron is excited by chemical reaction. And today we'll be focusing on photoluminescence, where the electron is excited by essentially light or photon absorption. And because of the nature of photoluminescence, where we only use a light to excite the electrons, it's contactless and non-destructive. And it is one of the big advantages of photoluminescence. And besides that, it's also a very powerful tool to gauge and measure defects in materials. So we can use it to measure the purity and the crystalline quality of materials, and also use photoluminescence to quantify the elemental composition of compound semiconductors and possibly other different things. So let's look at the mechanism of photoluminescence. So when we talk about an electron is excited to a different state, it's different for molecular materials and semiconductors. So for molecular materials, the electron is excited from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, as we can see in the graph here. So when the electron goes from the ground state, and when a light or a photon is absorbed, it will go through an excited state to the LUMO, which represents the lowest unoccupied molecular orbital. And when it goes back to the ground state, a light will be emitted from the material, and fluorescence will occur. And there's another types of photoluminescence. So the essential difference between these two photoluminescence effect is the state that the electron is excited to. So for the fluorescence, the electron is only excited to the singlet excited state, and for phosphorus, further converted to the triplet excited state. And when it goes back to the ground state, also emit light. And for semiconductors, the electron is excited from the valence band to the conduction band. And when the internal conversion happens, and after the electron relaxes to the ground state, a photon will also be emitted. And we can look at the Jablonski diagram for a more comprehensive illustration. So as we can see, the S0 in this graph represent the singlet ground state, and when the blue light, when light gets absorbed, which is represented by the blue line with arrows, the electron gets excited to a higher energy level. So as here represent the singlet excited state. So when the electron goes from S1, which is the first excited singlet state, to the ground state, um, the phenomena of fluorescence will happen, which is represented by the green lines. And for phosphorescence, um, the electron will be further converted to the triplet state, which is represented by the T here. So when it goes from this level to back to the ground state, phosphorescence will happen. And because there's actual step of conversion in the spin state, from the singlet excited state to the triplet excited state, the phosphorescence usually have a longer lifetime of emission than the fluorescence. So where can photoluminescence be applied to? So first, there are two main and more conventional applications, where the first is the spectroscopy, where the analysis is more quantitative, and we can derive a relation between the emission intensity and the wavelength. And there's another um, method that is used is called photoluminescence imaging, where we can construct images of the materials in different levels and layers, so we can have a more direct look at the materials, defects, and structures. And there are different categories of photoluminescence. Um, a big difference, one of the big categories that divides both two is the steady state photoluminescence and the time resolved photoluminescence. And the difference will be further discussed in Sam's part. And there's another spectroscopy that is very closely related to photoluminescence that is called ultraviolet visible spectroscopy, which is abbreviated by UV-Vis. And instead of focusing on analyzing the emission of light in photoluminescence, it focuses more on the absorbance of light in different wavelengths. And it will be utilized in the further discussion in Aloys's part about conjugated polymers. So let's get back to the two main methods of photoluminescence. So the first is spectroscopy, and the way we look at those graphs is we focus on two things. The first is the peak intensity, and the second is the peak wavelength. So if we look at this graph, at different amounts of iron doping in the cerium oxide, we can see that the peak intensity and the peak position differ by a little bit with each shifts in the composition. And by comparing those graphs and lines, we can have a peek into the material's impurity and defects. And also, similarly, on the graphs on the right side, we can see that with different levels of copper doping, the zinc sulfide will gives a different intensity and wavelength relation. And we can see in the more quantitative like peak wavelengths chart here, we can see that the peaks at different position varies depending on the composition. And with those information, we can analyze the defects in the materials. And the photoluminescence imaging is another method, as we mentioned before. It is more widely used in silicon solar cells analysis or silicon wafers. As we can see in those graphs, we can directly see from the graph what the defects look like. Um, for example, in the lighter region here, you can see it's possibly dislocation or some other kinds of defects. And it is a more direct way compared to photoluminescence spectroscopy because we don't need to analyze the curves and the relations quantitatively. And we can use this method to identify lots of different kinds of defects, which includes grain boundaries, dislocations, contaminations, and carrier lifetime.
So Harvey well explained the theories and fundamentals of PL. So in my part of the presentations, I'm going to introduce the instrumentations of two main PL systems, PL imaging and PL SPECT, which both of them demonstrated great abilities in detecting and analyzing defects. So first, I want to expand a little bit more about the PL imaging techniques in silicons. Personally, I found PL imaging fascinating because it is fast and you can visualize those typical defects in silicons, including precipitates, stacking plots, or dislocations. So how does it work? PL imaging relies on the radiative recombinations, which is the reverse process of the photogenerations of electron-hole pairs. Because silicon is an indirect semiconductors, the radiative recombination rate is typically quite low, which means that both the signals of the band-to-band and the defect-to-band are weak. But unfortunately, both of them are located in the NIR range, and we can use the band-pass optical filters coupled with high-sensitive cameras operating in the NIR wavelength range. And this approach helps us to enhance the signals and providing enough information about defects densities and type for quality controls. So next, I'm going to play a very short videos on the instrumentations of PL imaging. So here's the step one, external excitation by shining a light to generate access carriers. And here's step two, those access carriers are recombining through the band-to-band and band-to-defects process, emitting PL signals. And step three, those signals are captured by high-sensitive cameras, constructing a PL signal intensity map by moving the sample around. And eventually, you can get these beautiful images where you can clearly see the defects and possible identify the type of defects. So on the left, it shows an example of PL images observed on a silicon sample, embedding buried dislocations induced by ionic implantations and subsequent recovering anneal. So you can see the emitting defects are clearly visible here. And on the right, it compares between the selective etching analyzed, which is a well-known characterization techniques, and the PL imagings. And you can tell that the PL imagings can actually provide you accurate information about the defects. Okay, let's switch gears and start talking about PL spectra. The image on the left shows the simplified version of the spectra, always containing a source of radiations, a means of selecting a narrow band of radiations, and a detector. The image on the right is an actual experimental setup for measuring and analyzing the defects in gallium nitride, which Tai will go in depth talking about. So PR spectra is very similar to those absorption spectra, but take note that the detector cannot be placed directly along the axis from the source. Otherwise, it will receive both the transmitted radiations and the fluorescence or phosphorescence radiations. So there are two categories of PL, which both of them can provide some sort of information about the defects. First, steady-state PL. It studies the long-term average fluorescence of a sample upon the radiations, and it quantifies the intensity and wavelength profile of PL. So more importantly, the intensities could be related to the concentrations of defects, even though there is some limitations about this statement. And on the other hand, time-resolved PL studies the fluorescence of an example that is monitored as a function of time after the excitations by a light pulse. So why do we need a light pulse? Because it is necessary that a significant portion of the materials is rapidly excited all at once, so that the time-resolved decay of the luminescence can be measured from time zero. So the pulsed light sources can deliver a fast burst of photons to the sample and quickly generate a significant excited state populations. The time-resolved PL quantifies the PL lifetime by data fittings. Using these informations, we can potentially identify the type of defects and determine the concentration of defects. Because the lifetime of defect-related PL varies from sub-nanoseconds, microseconds, and even seconds for different defects. So next, I'm gonna hand the presentation over to Tai and let him talk about defects, luminescence, and gallium nitride.
Hello everyone, my name is Tai, and here we're gonna see how we could use photoluminescence in defect analysis for gallium nitride. So let's get started. Here is a little bit background for gallium nitride. So gallium nitride is a direct bandgap semiconductor with a bandgap around 3.5 eV at low temperature and 3.44 eV at room temperature. Because of their wide bandgap, they have attracted great interest over the past 2 decades as a material for blue and ultraviolet light emitting devices. But the point defects in gallium nitride hasn't been well understood. But photoluminescence is just a powerful tool that has been used in many previous research for the defect analysis for gallium nitride. So in this part, we're gonna see how we could analyze those PL data and what kind of information it tells us about the defect in the semiconductor. In the left diagram, it shows some common spectra for the gallium nitride from photoluminescence. As you can see, there is a huge peak around 3.4 EV. That is from the near band edge emission. Apart from this peak, we also have some other emission bands in the spectra. For example, here is a red band, here is a yellow band, and also we have green band, ultraviolet band. So those different bands actually correspond to different defects in the system. Different defects will create different energy levels in the band structure, and those recombination process just, give us photons with different energies. And here, the red diagram shows some other common defect-related bands in the PL. So just by simply looking at those spectrum from photoluminescence, we could get a general idea about like what types of defects could be there in the system. So next, we're gonna look closer into how we could analyze those data and what those data is telling us. So here, I want to firstly show like what those different bands tells us and what defects is responsible for the bands. And I will mainly focusing on the yellow band here, because this yellow band has been commonly observed in many previous research. And at first, people just didn't know like what causes this band. And with more recent findings, we actually have a better understanding about this band. So long story short, this band corresponds to the carbon-nitrogen defects in the system. So when some of the carbon atoms replace the nitrogen atoms in the system, they actually create some deep acceptor levels. And for N-type gallium nitride, the Fermi level is more towards the conduction band, right? So the acceptor levels are negatively charged. They are occupied by the electrons. So when we shine a light on the sample, we excite the electrons from the conduction band, from the valence band to the conduction band, and we're leaving some free holes in the valence band. Because the acceptor layer, the acceptor level are negatively charged, so they could easily attract those holes out of the valence band and capture those holes in the acceptor level. After that, the defects just become neutral, and the surrounding atoms just feel the change, and their equilibrium positions will also change, and the whole system should relax to a lower energy level. So in this diagram, after we excite the electron from A to B prime, and then the whole system will relax from B prime to C, just to accommodate this change. And from C, the electron actually could, recombine with the holes in the valence band, and that's gonna give us a radioactive emission, and the photon energy will be less than the direct band gap. And this actually corresponds to the yellow band we are talking about. So if you see something looks like a yellow band in your spectrum for carbon, for the gallium nitride, it's probably because of the carbon defects in the system. And after that, people actually developed this formula to estimate the yellow band shape in the system. I will not go into the details about this model, but just want to say if you fit the experimental data with this equation, you could potentially get some parameters in the equation, and that could be useful for other analysis as well. So this slide just shows us how we could, using the band in the spectra to, get some information about the defects in the system. And apart from the band, we actually could get some more specific information about the defect themselves. For example, we could get the hole capture coefficient, the electron capture coefficient, and also the ionization energy about the defects. So the idea here is that we have the formula that is describing the photoluminescence intensity about a specific band as a function of the temperature. And this formula just includes a lot of important parameters about the defect itself. So by fitting the PL intensity dependence with temperature from the experiment, using this equation, we could actually find the hole capture coefficient and also the ionization energy for the defects we're looking at. And apart from those two important parameters, we also have another formula for the electron capture coefficient of the defect, and it is directly related to the photoluminescence lifetime and also the free electron concentration in the system. The lifetime could be directly measured using time-resolved photoluminescence, and the free electron concentration could be easily measured by the Hall effect experiment. And the two diagrams just show some real experiment data for different band. So it just demonstrates that we could calculate those important parameters for the defects in the band using the technique we mentioned before. And finally, we could estimate the point defect concentrations in the semiconductor using the photoluminescence data. The idea here is that we only have limited amount of defects in the sample. So with increasing excitation intensity, it is possible that we saturate the defects with photo-generated charge carriers. That means there should be a critical excitation intensity above which the photoluminescence intensity shouldn't increase. And from some experimental data showing in this diagram, we can easily see that when we're increasing the excitation intensity, at some point, the quantum efficiency just drops from that critical excitation intensity, right? That is because we couldn't emit more photons out of the system with the higher excitation intensity because the defects has been saturated. So using the relationship we have here, we could see that the critical intensity is directly related to the defect concentration. If we know the values for other parameters, we could easily calculate the concentration based on the experimental data we have. For those different parameters, actually we have different methods to estimate them using the photoluminescence data as well. So it just provided us with a very easy way to really get the concentrations of defects within the semiconductor. And also if at lower temperature, we ignore the quenching effects, we could also derive this formula here. It describes the ratio of the two defect concentrations using the PL intensity. So that also provide us with another way to estimate the defect concentration based on the other type of defect in this system. So that could be very useful for the defect analysis as well. So here I'm just covering like a few use case of photoluminescence data for defect analysis here. But as you can see, it's really powerful for the defect analysis. And I just want to bring this up, and hopefully everyone could appreciate the usefulness of photoluminescence in semiconductor defect analysis.
Hi, I'm Aloysius, and I will now move on to talk about conductive polymers, a topic we touched on very briefly in class. Hopefully, after this presentation, we can have a greater understanding of conductive polymers. So what are conductive polymers? Conductive polymers are pi-conjugated compounds with controllable electrical conductivity over a wide range from insulator to metal by chemically or electrochemically doping its backbone. These polymers see applications in many areas, including photovoltaic cell, chemical sensor, storage battery, and membrane gas separation. The main types of conductive polymers are polyacetylene, the first conducting polymer. However, polyacetylene is unprocessable as it is unstable in air and insoluble in solvents. Polypyrrole, polythiophene, polyphenylene, and polyaniline. For the rest of my presentation, I'll be talking about polyaniline. Polyaniline has attracted global interest because of its stability in air and ease of synthesis. In addition, it has flexible control of electrical features with charge transfer doping, protonation, and its inherent variable oxidation states. During the polymerization of the aniline monomer, polyaniline transforms into one of the three oxidation states: completely reduced leucoemeridine base state, half oxidized emeridine base state, and the completely oxidized polygranulin base state. The emeridine base state is a semiconductor and is composed of an alternating sequence of 2 benzenoid units and 1 quinoid unit. The leucoemeridine base state only has benzenoid units, and the polygranulin base state quinoid units. The emeridine base state can be non-redox doped with acid to yield the conductive emeridine state of polyaniline. Different acids such as PTSA, p-toluene sulfonic acid, camphor sulfonic acid, acetic acid, and hydrochloric acid can be used. Here, the imine nitrogen atoms of the quinoid moiety are protonated to give a polaronic form where both spin and charge are delocalized along the entire polymer backbone, thereby enabling greater conductivity. So how do we synthesize polyaniline? There are various synthesis methods for polyaniline: electrochemical polymerization and chemical polymerization. And within the chemical polymerization subcategory, there's traditional polymerization. For instance, where the oxidative chemical polymerization occurs in an aqueous acidic medium to form the emeridine salt. Hard template polymerization, which employs a physical template such as anodized alumina oxide and mesoporous silica or carbon as a scaffold for the growth of conducting polymers, and interfacial polymerization. Now, let's link it back to our main topic, photoluminescence. Before we discuss the photoluminescence of polyaniline, it is useful to know the UV-vis absorbance spectra. This is the UV-vis absorbance spectra of emeridine base and the leucoemeridine base state. The two absorbance peaks for the emeridine base state at 337 nanometers and 666 nanometers correspond to the pi to pi star transition of the benzenoid segments and the pi to polaron band transition of quinoid segments, respectively. The loss of the absorbance peak at 666 nanometers for the leucoemeridine base state is expected due to the loss of the quinoid structure. Here, it is important to note that the valence and conduction bands are formed by the pi and pi star orbital respectively. Thus, the pi star transition of the benzenoid segments tell us the band gap of the material. With the absorbance spectra, we now move on to discuss the photoluminescence of polyaniline. The excitation wavelength was set at 300 nanometers, which falls within the pi to pi star absorption envelope of the benzenoid units, as the photoluminescence structure in polyaniline is the benzenoid unit. On the other hand, quinoid units do not fluoresce. Results of this study, as you can see here, demonstrate that the leucoemeridine base state of polyaniline exhibits a photoluminescence spectrum with wavelength maxima of about 410 nanometers. When the leucoemeridine base is oxidized, the photoluminescence intensity decreases until there's no measurable signal when the polyaniline reaches its emeridine base oxidation state. This is because when the polyaniline is oxidized from its fully reduced leucoemeridine base state to its half oxidized emeridine base state, benzenoid units are converted to quinoid units. The decrease in the photoluminescence spectrum can be attributed to the decreased concentration of the photoluminescent benzene units. In addition, intra-chain energy migration can occur, thereby allowing the quinoid groups to act as excitation traps and quench the photoluminescence from the benzene units. Thus, the photoluminescence of polyaniline is proportional to the concentration of benzene groups, and it is quenched when such a group is adjacent to a quinoid group. It is worth noting that many conductive polymers exhibit photoluminescence only in their fully reduced states. Earlier, we talked about the emeraldine salt being the conductive state of polyaniline. So what happens to the photoluminescence when the semiconducting emeraldine-based state of polyaniline is doped to yield conducting emeraldine salt form? When a form of emeraldine base that exhibits photoluminescence is doped with HCl vapor, the photoluminescence spectrum remains. However, the position of the peak is shifted from a wavelength maximum of 401 to 467 nanometers. Now, why is there a rate shift in the photoluminescence spectra upon doping with acid? Since the photoluminescence spectrum is related to the pi-to-pi star absorbance transition, a change in the energy gap will result in a change in the photoluminescence spectrum. When a form of polyaniline is doped from its emeraldine base state to its emeraldine salt state, the energy gap of the benzenoid pi-to-pi star transition decreases. As can be seen from the rate shift of the minimum from 444 nanometers to 523 nanometers associated with the benzenoid pi-to-pi star absorbance in the UV spectrum. The decrease in the energy gap leads to a decrease in the photoluminescence peak at 401 nanometers. The 401 nanometers peak characteristic of emeraldine base begins to disappear, and the 467 nanometers peak characteristic of the emeraldine salt appears. I hope you now have a greater understanding of conductive polymers. I'll now hand over to the next speaker.
Hello everyone, my name is Jun Wang. In this part, I will talk about PL's application in 2D materials. We all know that 2D materials possess atomic thin geometry and remarkable properties and are the star materials for the fundamental researches. Defects in 2D materials are critical to understand their excellent properties. The figure shows various defect structures in 2D materials like the dopants, the boundary, and the vacancy. I will briefly introduce the fundamental mechanisms between defect and the PL in 2D materials. First, the doping defects. Doping is one of the dominant defects to affect PL. I listed two typical examples to show how it works. The first example is MOS2 with erbium dopant. Figure C shows that under 488 nanometer excitation, the PL signal of pristine MOS2 and MOS2 erbium are both located at the same place. Figure D shows that under 980 nanometer, the up conversion emission was observed in MOS2 erbium, while the other emission peaks at shorter wavelengths were not. This is because radiation transitions with higher photon energies than MOS2 bandgap are absorbed by the host. We can figure out that the erbium dopant changes the original properties of MOS2 by changing the process of the energy transitions, and it results in both up conversion and the down conversion PL. The other example is niobium doped MOS2. In this situation, the impurities will also lead to the structure change. Like figure A, the introduction of niobium can lead to the MOS2 structure change from 2H to 3R. And 3R stacks with a slightly shorter interlayer spacing compared to 2H. So the PL of 3R biolayer is a little redshift. We can also see that with higher niobium concentration lead to more significant redshift. This is because the niobium in impurity states will cause the valence band modification. we can see that there is a level cross between the valence band and the EI, which is the impurity level induced by the MB replacing MO. The MOS2 band restructures with a strong band crossing interaction with MB doping concentration, thus shows the significant redshift. While figure C is for both bulk and bilayer cases, and in monolayer MOS2, the impurity states locate above the valence band without crossing, forming the isolated in-gap impurity states. This will also result in a few notable changes. Then, the green boundary defect. Figure A shows the atomic structure of green boundaries. The green boundary has a plus or minus 20 degrees incline, and both tilt and mirror twin boundaries can be found in these films. So, in order to detect impacts of green boundaries on 2D materials, we compare the PL mappings between the samples with highly symmetric mirror twin boundary and the sample with a tilted boundary. The black arrows point out both ends of the boundaries. So we can see obvious differences in quantum yield, the blue shift of PL peak, and the peak weights between the twin boundaries and the tilted boundaries. All these PL distinctions proves that different type of green boundaries affect PL properties of 2D materials differently and seriously. This is because green boundaries may introduce some local doping. Doping will change charge density, therefore determines the PL intensity. In this example, rich MO atoms aggregating at the twin mirror interface and increase the charge density and to decrease the PL intensity. Sulfur atoms gathering at the tilted interface boundary decrease the charge density and enhance the PL intensity. Thus, we can know that when the green boundary is implanted into the 2D materials, it will introduce mid-gap states specially localized at the boundaries. Next, let's see heterostructure, which is also I'm most interested in. Lateral heterostructure is similar with green boundaries, but the interface is more smooth with fewer weaknesses. Take lateral heterojunction considered by WSE2 and MOS2 as an example. Figure D shows the PL spectra of these 4 points beginning from the WSE2 to sample central area of MOS2 across the interface. Since the interface is particularly sharp, all PL peaks locate around the 1.57 and 1.51 EV, which means that they are all emitted from WSE2 and MOSE2, nothing else. While for the gradual interface, the PL peaks increase from 1.57 EV at 0.1 and gradually to the larger energy at 0.6. The PL intensity in the gradual zone, this zone, is obviously stronger than the Princeton WSE2 zone and the MOSE2 zone, which means more charge is generated in such interface. Researchers regard the different photon energy beyond the MOSE2 and WSE2 as emitting from additional alloy, this alloy, which could generate excitons with intermediate energies. Therefore, since the sharp interface doesn't have such extra alloy, all the photons emerge only from the WSE2 and MOSE2. We can see the difference between the gradual and sharp interfaces more easily from this figure J. PL spectra of this is a PL spectra of a sharp heterostructure measured under extremely low temperature. Similarly, only excitons from WSE2 and MOSE2 appeared at the point of 1 to 5, like the WSE2 and then the MOSE2 and then the WSE2 back, which don't have the intermediate energy peaks like shown in gradual interface PL figure. Thus, the absence of intermediate energy peak proves the sharp interface. Then what about the vertical heterostructure? Take PN junction constituted by stacked SN, S2 over WSE2 as an example. From figure E, we can see that the vertical junction quenches most of the PL intensity, while the PL is obviously stimulated from a bottom monolayer of WaC2. Figure F shows the pristine WaC2 PL peak, while there's no PL of heterojunction is detected. Such strong PL quenchage comes from the efficient interlayer charge transfer between the bottom and the top layers. It can be interpreted mainly according to band alignment offset. Both conduction band minimum and the valence band maximum of SnS2 is lower than those of WaC2, conducting a staggered broken bandgap structure. Therefore, right in the connected interface, the stimulated electrons tend to transfer towards CBM of SnS2, whereas the holes generated at SnS2 are more likely to move to WaC2. So the possibility of excitons formation and their recombination is seriously decreased. So there's no PL. In summary, in 2D materials, bandgap can be adjusted by introducing in-gap levels or bending levels, by introducing dopants, grain boundaries, and also the vacancies. The interactions of different materials with different bandgap, such as heterostructures, can also create novel photoelectric properties, such as PL quenching. In the end, here is the conclusion of our group's presentation. We first explain the fundamentals of PL and also talk about PL superiority of technique in defect analysis, exemplified by its application in conventional semiconductors, semiconducting polymer, and 2D materials. So thanks for listening. Please tell us if you have any questions.